Hello. In this video I'm going to be going through this problem here. So I'll first read this out to you. Uranium-238 has a very long half-life and decays through a series of daughter products, ending with a stable isotope of lead. Very old samples of uranium ore, which have not undergone physical or chemical changes, would be expected to show an equilibrium between the daughter elements, provided that their half-life was considerably shorter than that of uranium. Analysis of an ore of uranium shows that for each 1 gram of uranium, there is 0.3 micrograms of radium-226. The half-life of radium is 1,602 years, and the question is asking us to work out the half-life of uranium. Okay, so the key part of this question is the fact that it says very old samples of uranium would be expected to show an equilibrium between the daughter elements. So the important part is equilibrium, so we need to understand this concept first. So first I'm going to show you the actual decay series of uranium-238. So you can see it here. So it starts off with uranium, and you can see it goes through several decays. It goes through lots of different elements, and you can see here there's radium-226, which was mentioned in the question, and it finally ends up as stable lead-206. And the question told us that very old samples of uranium would be expected to show an equilibrium between the daughter elements. So if we just imagined any radioactive element, so I'm going to call it element A, and this element A, it decays into another element, which I'm going to call B. And B decays into another element, C. And we can see from this that element A is made up of a number of unstable nuclei, and it is decaying into element B. So we can write that a change in number of nuclei of element A in a unit time, that decrease in the number of nuclei, that is equal to the activity of this sample, so it's known as the activity. So we can write dNA, so Na is the number of nuclei of element A, dt, that is equal to minus lambda A Na. So the activity of a radioactive sample, that is proportional to the initial number of nuclei in that sample, so in this case Na, and the constant of proportionality is known as the decay constant, which is expressed as lambda, so lambda A. And we can also write something similar for element B, so a change in the number of nuclei of element B in a unit time, so dNB dt. Now that's going to be equal to the production of element B, which happened as a cause of the decay of element A, so it's going to be equal to the same lambda A Na, but from that we need to subtract element B's own decay, because B is decaying into C. So we'd subtract lambda B and B. Now, the question tells us that we are looking at a situation which shows equilibrium between the daughter elements. And equilibrium is something that happens when the half-life of the parent isotope, so in this case A, is much greater than the half-life of the daughter isotope B. And when A has a much greater half-life, this means that it decays very slowly, and so its rate of decay is almost constant. But the rate of decay of A is the same as the rate of production of B, and so the rate of production of B is also approximately constant. And so as the quantity of B increases, the rate of decay of B into C also increases, and eventually the rate of decay of B becomes equal to the rate of production of B, or the rate of decay of A. And at this point, the situation is called equilibrium, or secular equilibrium. And at this point, the quantity of B remains constant. And so if the quantity of B remains constant, at this point we can write dNB dt is equal to 0. And obviously if dNB dt is equal to 0, we can see from this equation here that lambda A NA must equal lambda B NB. So that's quite an important equation. Now, if we apply this to our question, which involves the radioactivity series of uranium-238, the question tells us that this sample of uranium is very old, and it shows an equilibrium between the daughter elements. So, for example, between thorium, radium, and radon, the system shows an equilibrium. So that means the quantity of radium in the sample, it remains constant, which means that the rate of decay of radium is equal to the rate of decay of the element before it, thorium. But this applies to the entire series, so we can say that the rate of decay of radium is equal to the rate of decay of the original uranium. So we have our equation here, and if we apply it to our question, we can write that lambda U for uranium, so uranium in this case is the parent isotope and radium is the daughter isotope. So the activity of the parent isotope, lambda U NU, that is equal to the activity of the daughter isotope, radium, so it is equal to lambda RA NRA. Now the question is asking us to calculate the half-life of the uranium. So what we need to do is work out the value of lambda U. And we can see that lambda U is equal to lambda RA NA NRA over NU. Yeah, and the reason we need to work out the value of lambda U is because there is a relationship between the value of lambda and the half-life of a substance. So as you can see in this diagram here, when as A decays into B and B decays into C, there is something called an exponential decay law in both of these decay processes, and we can write that as n, which is the number of nuclei in a sample at any moment. N equals n0, which is the initial number of nuclei in a sample. So n equals n0 e to the power minus lambda t, where here lambda is the same decay constant that we've been using. And we can see from this that when t is equal to the half-life of any particular sample, so when t equals t half-life, we know that after one half-life has passed, the number of nuclei left in the sample is going to be exactly half of what there was initially. So when t equals t half-life, n is equal to n0 over 2. And if we use this, we can show that after some calculations, we can show that lambda, the decay constant, is equal to ln, so the natural log of 2 over t half-life. And so that's the equation we're going to need to use in this question once we have worked out the value of lambda u, so the value of the decay constant for uranium. Okay, so we can work out the values of lambda Ra, nRa and nu, because the question gives us the value of the half-life of radium. It was 1,602 years. And we have the equation lambda equals ln2 over t half-life. So we can see that lambda Ra is equal to ln2 over 1,602. And we can also work out nRa and nu, because the question tells us, so for radium, it tells us the mass number of the radium is 226. So we know that 226 grams of radium is going to be equal to, it's going to include or contain 1 mole of nuclei of radium. So it's going to contain Avogadro's number of nuclei. So if I use A to represent Avogadro's number, so it's going to contain A nuclei. And the question tells us that in this sample of uranium there is, for each 1 gram of uranium there is 0.3 micrograms of radium. So we need to work out how many radium nuclei there are in 0.3 micrograms. So in 0.3 micrograms of radium, there is going to be A times 0.3 times 10 to the power minus 6 over 226 nuclei. So that is the value of nRa. And similarly we can work out how many uranium nuclei there are in 1 gram, so the value of Nu. So the question tells us the mass number of uranium is 238. So we know that 238 grams of uranium has a Avogadro's number of nuclei. So 1 gram of uranium will contain A over 238 nuclei. So that's the value of Nu. And now so we have the values of NRA, Nu, and lambda Ra. So if we substitute all of those into this equation, then we get lambda U equals ln 2 times 0.3 times 10 to the power minus 6 times 238 over 226 times 1602, so the A's, the Avogadro number, it actually cancels out. And we know that, so the question was asking us for the half-life of uranium, so we know that T half-life of uranium is equal to, so we know the relationship between the value of lambda and half-life for any radioactive sample, so we know that T half-life is equal to ln 2 over lambda U. And we now know the value of lambda U, so if we substitute that in, T half-life of U, of uranium, becomes equal to 226 times 1602 over 0.3 times 10 to the power minus 6 times 238. So actually ln 2 cancels out as well. And if you do this calculation, you'll see that the half-life of uranium comes out to be 5.07 times 10 to the power minus times 10 to the power 9, so billions of years. And this is years. And yes, that's the final answer.